So yeah, like I was saying, I was waxing eloquent about how much I love. Oh, my love for bee trees is like a garden or something like that. But anyway, yeah, bee trees are really neat. And one of the things that we don't really talk about here is the fact that you can actually use them for sequential tuple files. And you will see that on the fifth assignment. I think I mentioned a little bit about this last time. But what we're doing right now is talking about B trees specifically as used for indexes. And so when you look at all of this, think about how you can generalize the concept. We have this file pointer thing that we have in the leaf nodes, but you can actually take that and modify it just slightly and turn it into a general sequential file format as well. And once you get the B tree code and you get it working, because you'll have to finish a few parts of it, then you can actually use B trees as sequential files as well. So if you have things like sort merge nodes and things like that, then you can actually try them out and see if they work properly on joins and things like that, that might require sorted input. So it's pretty nifty, and that's why I get so excited about them. So we talked about, remember we talked about querying and insertion last time. Querying is pretty straightforward. We navigate the non-leaves. We look at, we have a value that we're searching for, and we compare it to each key in sequence in the non-leaf or in the leaf. And if it's less than, we follow the left pointer. If it's equal, we follow the right pointer. And we try to take a step forward. And if we can't take a step forward anymore, then we have to follow the rightmost pointer because the value is going to be in there. Now we just repeat this until we hit a leaf node. And what you'll notice is that process of navigating from the root of the B tree down to a leaf node appears in querying, in insertion, and in deletion. Because we always have to find where the record should go, or where the record is that we're removing, or the record is that we want to use to look up something. So this process of navigating from root to leaf is quite important. Insertion wasn't that much more complicated. Most of the time we're inserting into a non-full node, so we don't have to worry about doing anything. But when we do need to add a value to a full node, then we have to split it. And that process wasn't terribly complicated. Like I say here, we have to add the new node into the parent node's pointer list. And the only detail there is we have to make sure to propagate up the appropriate key. And when we take a node and split it into two, the right node, its first key value is what we propagate up to the parent. Just because of the thing that we said, always go right on equality, as opposed to going left on equality. That's the reason why we propagate up the first key of the right child. If we did left on equality, I think we propagate the last key of the left child up. So it just varies a little bit. Anyway, so this was the general principle. This is what I was just explaining. We write this up as like if splitting node n and into n and n prime, where n comes before n prime, then n prime's first key is the thing that we actually propagate up. So n prime dot k1, this is the way that we'll write it, parent n prime. Okay? So that's pretty straightforward. And n and n prime are, of course, siblings, so they can share values, and that will become very important as we start talking about deletion. The reason why deletion is challenging is just because of this non-full requirement. We have to always have at least half of our node full, as long as it's not the root. Because remember that sometimes we just don't have enough space for, or I should say we don't have enough data for the root node to be full. There was the one caveat which was mentioned in a question that the root node may contain just one pointer and no keys, in which case we don't need it anymore, so we can just toss it out. But we'll see that as an example as we go through this discussion. So we had this tree with n equals 4, which means that the non-leaves have to have at least 2 pointers, so you can see that all of our non-leaves are, or I should say inner nodes, because non-leaf is not very easy to roll off the tongue. But all of our inner nodes have at least 2 pointers, so we know that they're all full enough. And our leaves have to have at least 2 pointer and key pairs. So we have this thing that the leaves always have this last pointer, which we don't count in our fullness counts. But the inner nodes, we don't have a next pointer for those. So we have 4 pointers and 3 keys. The leaves have 4 pointers, or I should say 3 pointers and 3 keys. Okay, so we'll go through this, but at least 2 pointers is the caveat. And yeah, in these cases where we don't hit our size constraints, we're happy. And the example that we looked at last time is we want to delete dot, And that's all we have to do, because the leaf that it was in was already full enough that when we remove dot, it doesn't affect the tree structure. And this is going to be the bulk of the situations when you delete from a B tree, in fact, because you're going to expect to have at least 100, maybe 400 values in each B tree node. So when you delete stuff, most of the time you're not going to run into these size constraints, which is really nice because it's going to be fast. You just navigate down. The early nodes in the structure, the early inner nodes, will likely be in cache, so it'll be super fast. You don't even need to load them. And the specific leaf that you're looking for, you delete the value, and that's all you really need to do. You don't need to care about anything after that. So if we have a node that becomes too empty, then we have to start thinking about, well, how do I satisfy this fullness requirement that I must be at least half full? And we had a couple of options. One option is that we can steal values from a sibling, because it may be that the sibling is a lot more than half full, so I'll just move some values over from the sibling, and now I'm still at least half full. Everybody's happy. We've maintained the constraint, the size constraint, and we haven't incurred extra IOs from restructuring the tree. Or we might have to coalesce if we don't have enough values to redistribute. So redistributing is our preferred approach, but if we don't have enough data for that, then we go ahead and coalesce. So those are our two options. So sibling has extra values, we redistribute values. So this is an example where we could redistribute. If we delete rat or we delete tin, then we could pull values from the right sibling, which is the only sibling that node has. Because notice the node to the left of it is not a sibling because it has a different parent. So we pull across bat maybe, and now we have a node that satisfies the fullness requirement again. So that's one option. We could redistribute. We could also coalesce. And if we deleted gut from the second leaf node, then we have an option of either coalescing not into bibcat or into offpit. You could choose one or the other. All right? So these are our two options that we have. And you can see that this is where a lot of the complexity of B trees arise. And I haven't figured out quite how to make a B tree implementation that's nice and clean and simple, because you have such a difference between inner nodes and leaf nodes. So you end up with code that's like almost the same, but not quite. And I think that's where standard B trees, without the plus, standard B trees would be a little bit nicer, because the implementation, all of the nodes are identical. So standard B trees would allow you to avoid having similar but not identical code. B plus trees, though, they tend to have this problem that inner nodes are manipulated slightly differently than leaf nodes, so the code is almost the same but not quite, and it can end up being quite frustrating. You get that code smell. I don't know if you guys have heard of code smells, but there's like, oh, this code is a little bit off. It's not designed properly, or it's not implemented properly because it has this unsavory characteristic about it. They call it a code smell. Or a design anti-pattern would be another way of describing it. Anyway, so yeah, we have the challenge that we could combine not with the left one or the right one. So we have to check all these possible cases and then respond accordingly when it comes to moving things around. And you'll see sort of the consequences of that when you look at the B-tree code in NanoDB. So when we redistribute or we coalesce, obviously parents are affected as well. And sometimes we have to remove things from the parent. If we coalesce, then we're removing a child. So clearly we have to modify the parent. And if the parent becomes less than half full, now we have to redistribute or coalesce at the parent level. And so it can propagate all the way up the tree. And interestingly, what can happen is if the B tree becomes empty enough, you get rid of the root. And so the depth of the tree shrinks by 1. And you incur 1 less I/O to do lookups, which is kind of nice because you can use that to, sort of as your data size grows or shrinks, the amount of I/O required to access the index also grows and shrinks correspondingly, which is nice. Yeah, deleting and rearranging leaf nodes, updates to parents are more straightforward. When you're deleting or rearranging non-leaf nodes, the updates are more involved. And we'll start looking at some of these things because it is rather complex. Once you see the patterns, though, you'll be like, okay, I get the pattern. And that's why it doesn't scare me anymore. But the first time I was learning this stuff, it was a little bit scary. Okay, so I delete tin. I cannot coalesce. So we only have one option, which is nice. I kind of constructed it that way on purpose. But we cannot coalesce because the right sibling has no space to move rat over there. But that leaf is now under fold. So what we need to do is steal that is probably the one that we'll want to steal. Remember, we have to keep the total ordering of all the entries in the B tree as well. So we can only steal that. We can't steal, I mean, that's not true. We could steal, well, actually, we can't steal yak as well because that would cause the right sibling to be under full. But the point that I'm trying to get at is we must take that. We can't take yat and we can't take zat because that would put things out of order. So we would move that across. And now we have this situation. Yeah, so we have a problem now. That is incorrect, right? We'd have a problem. So clearly we have to modify the parent node. Now what value should go between the pointers in the parent node now? Yeah, the general rule is just like it was with insertion. The right sibling's first key goes into the parent. How hard is that? Okay, so the first thing we do is we slide that over and we migrate yak up. Now, why am I spelling this out? Well, because it may be that we don't just move one thing. We may have a situation where keys can vary in size. And we have, the average size might be like 10 bytes, but then every once in a while we have like a 100-byte key. And so we remove a 100-byte key, and now I can slide a bunch of things over. And so again, the rule is very simple. I always propagate the right sibling's first key value up to the parent. Okay? That's the rule. Okay, so I go ahead and update this. And this is basically saying exactly what I had before. I think so now that would become yak. So like it says here, when you're moving things back and forth, you always need to make sure the parent, and again, this is true even if you're moving stuff from the left to the right. I want to make sure that I'm really clear about it, because you'll have to do this in the assignment. Whether you move things from right to left or you move things from left to right, the right node's first key is what goes into the parent, always. Because we go right on equality. If we went left on equality, we'd have to move the left node's last key up, but we don't care. We're going to do the right node's first key. Okay, so this is basically what we end up with. Are there any questions about this easy case? All right, so far we haven't had to modify the inner node. That's besides replacing a key, but we haven't had to do anything worse than that. Now let's talk about a slightly more complicated situation. We remove gut. Everybody wants to get rid of their gut, and so we do. And now we have just not, and we have a choice that we can either move that value left or we can move that value right. Let's look at both examples. So we're going to coalesce left. And if we do that, then we end up with not in the left node. And now we notice that the parent node has a dangling pointer. It no longer points to an existing node in the B tree. But it also has a value that we don't really need anymore. So the question is, do we want to get rid of dot or do we want to get rid of off when it comes to updating the parent? We have to think about this. Now remember, if we're looking for the entry with the key value off, we'd start at the top and we'd say, ooh, off is less than rat, so I follow the left pointer and I get in here. And if I look at this stuff, I would say, ooh, off is equal to off, so I follow the right pointer and I end up in the node. So it seems like we probably need to eliminate dot. Because if I happen to be searching for dot, I definitely don't want to end up in La La Land. Which sometimes my programs do. Like, my programs do it too. You shouldn't feel, not that embarrassed when things crash, because my programs crash too. Yes?
I thought they need to be in order, but so as example, right now, not is greater than not, but it's pointing towards the left.
No, within a node, all the key values need to be in order. So the fact so that's another issue. That's another reason. What you're stating is just another reason why we need to eliminate dot. But yeah, because really the constraint is that the last value in our first leaf, so bibcat not, needs to be, all of those values need to be less than the key value that we have following our node's pointer. So yeah, that's another reason, yet another reason why we need to get rid of dot. Okay, so this is after coalesce. So we need to modify the parent node, and we end up with something like this. Okay? So that was pretty straightforward. Yes? In this lab, do you end up with a lot of null pointer exceptions? You could. My code doesn't. Oh, the debugging process is hideous, I have to say. But you know, there is a, you probably noticed that in the heap file, there's a sanity check on data pages, which makes sure that all of the slot offsets are in order and all of that. It goes and checks a bunch of things like that to make sure that everything is okay. We have similar code for B-trees, which actually is far more complete in its checking because we want to, for example, make sure that every inner node has only one pointer to it. That would be a good thing to enforce. B-trees should not be DAGs. If they are, there's a bug. Also, to make sure that every leaf node has only one pointer to it, and so forth. Make sure that every node's keys are in order. So we have some code that goes through and checks this kind of stuff. And we have a sequence of tests which builds things up relatively slowly again, just like the heap file insert and then insert and delete. So we have build a B-tree that's one page, and so basically the keys stay in order. Okay, keys stay in order. Insert and delete, make sure the keys stay in order. Now do 2 pages. So now you have a parent, and you have to make sure that the sibling children stay in order and all of that stuff, but you only have one parent, so we don't worry about coalescing parents and so forth. We worry about splitting and coalescing children. So you have various tests that stage the process. And, of course, you turn on the obscene logging, and this is unfortunately the reality when you debug file system data structures. You turn on the logging, and you find out where it starts going wrong, and you trace back to see if you can find the issue. So, sorry. There's not a better way just because of the way this kind of code is usually written. Now, I did talk about this, and you've already gotten me distracted, so I'm going to be like talking about this instead of the lecture for a little bit. But that's fine. The thing that I mentioned when we were talking about heap files is that it would be really nifty to have a way of specifying file system data structures in a way that maps things more naturally to values or classes in memory, or structs, if you will, if you're in C. And languages like Erlang have this really cool ability to do pattern matching on binary data, which is really nifty. It makes this kind of thing super simple. In fact, that's why I think it was Motorola did an experiment. They did a comparison where they took some of their routing hardware, packet routing hardware, and the code was written in C++, and they rewrote it all in Erlang using binaries and pattern matching on binaries and things like that. And they found that their code shrank to like 10% of the size of the C++ code. And when you write these kinds of systems, you get a lot of code from just unpacking and packing data into a binary representation. And so having a way of doing that more efficiently would allow you to avoid a whole bunch of bugs. And perhaps it would allow you to debug things more easily and so forth. But, you know, I mean, should I make Erlang a requirement for the class? I don't know. See, there's drawbacks, right? I could have you use a language that everybody uses, and then you have to go through the pain of it, which is good because then it's instructive. Or I could have people use a language that isn't widely used, and then that also in some ways affects the quality of the education. So, balancing it. But anyway, it's an interesting side topic. That's why I spend the time on it. But yeah, that's unfortunately part of the reality. But I do try to stage it in the testing so that it will be not too hideous for you. Okay, any other questions about this? All right, yeah. I've long noted that it's easy for me to get distracted with good questions. So, all right, so we coalesced left. Now let's look at coalescing right. Now again, we have a dangling pointer, and we have our right thing. And you might notice a couple of issues already. right? Again, having off between these two pointers is now incorrect because if we happen to be looking for not instead of off, we'll end up in the wrong place. In fact, we'll end up in La La Land because we'll try to follow that middle pointer. So off probably doesn't belong, and our middle pointer also needs to be removed. So hopefully you see the pattern. When I remove something, and then I coalesce left, I get rid of the key that's to the left of the dangling pointer. If I coalesce right, then I get rid of the key that's to the right of the dangling pointer. So it's a pretty straightforward mechanism to implement. Okay? Questions? So that's coalescing. That's coalescing in leaves where I don't have to do anything more complicated than that. But you can see how that process is pretty straightforward. And if I had to do the same thing at inner nodes, then I can just propagate this up. So it turns out to not be horrible, except for the little implementation issue that I mentioned earlier, that you have code for leaves and inner nodes that's pretty similar, and that's a non-ideal approach for implementation. Okay, so coalescing two siblings, where n is the predecessor to n prime, so n is to the left of n prime. The two siblings are separated by a key, and we need to basically eliminate the pointer and the key that's sandwiched between the two. Okay? So that's pretty straightforward. Like I said, this mechanism is easily implemented in a B-tree implementation. There's not really a lot to it. Now, deleted internal nodes. Yeah, we're not going to show record pointers anymore just because it's too complicated. But let's say that we get rid of that. And now earn is not enough. We need to have at least one more value. So again, we can coalesce. We can't redistribute because yak zap doesn't have enough. But we can coalesce. And like I say here, we know how to do that. And interestingly enough, when we do that, we end up with a situation like this. Notice now I have an inner node with no keys in it. And if I have no keys, then that should be an indication that I don't need that node anymore. Because all it is an extra step along the way to the leaf that I actually care about. So in this situation, I have to do something else. Now what are my options here? Can I redistribute on the second level of nodes? I could move a pointer from the dot off pop inner node. It's always fun to read these keys. To the right one. And then there will be enough pointers. Because dot off will have 3 pointers. And the right node would have 2. And that would be okay. Could I coalesce? Yes. I might be able to get rid of one level, yeah. Interestingly enough, you'll probably frequently notice situations where you could take the B tree and rearrange values to actually make it smaller. Again, I'll probably make that extra credit on the 5th assignment, but there is an optimize command, and you can use that optimize command to rearrange data structures to be faster. We talked about this a little bit last time, but this is another characteristic of it. When you remove nodes or you remove data from a B tree, you may end up with a situation where you have a lot of free space. And if you rearrange the data in the B tree, you could end up with a much more efficient representation. So I will leave that as an exercise for the students that are interested. Yeah, these are the situations. Yeah, in this situation we can't coalesce because we already have 4 pointers. So we can't move that pointer left. We don't have space for it. So we can redistribute. And so what we're going to do is, like it says here, we're going to have the right node point to pop rat and earn yak zap. The left node will only point to the first 3 leaves. So we end up with something like this. And now we have an interesting question of what do we actually put in between the 2 pointers on the right node? And what do we do with pop? Earn is a good idea. Can we move pop straight across? What about that option? Let's discuss that option first. Is that allowed? Why is it not allowed? is less than earn. Why would that be a problem? Like which earn? Because there's a top earn and a bottom earn. Okay, the top one we don't care about so much. But why do we care about not being able to? Oh yeah, so I see what you're saying. So you can't move pop to the right because it would be less than earn. Yeah, I agree with that. Actually, that makes perfect sense. Okay, so we can't move pop across. But yeah, earn we can definitely move. So where do we move the search key values? So you'll notice that you have this sort of rotate through the parent operation now. When I want to move something to the right, I can't just move it straight across. I have to migrate the key through the parent. So pop goes up and earn goes right. And so this again is where it gets a little bit complicated because right now we're only moving one thing. But imagine a situation where we're moving 9 things. Well, then you need to think about, okay, what actually goes into the parent and what stuff do I move across? And the nice thing about it is moving 9 things collectively ends up with the same result as moving them individually. So you move one and it goes up and the up thing goes to the right and then you move the second one up and it goes to the right. So basically what you could do is figure out if I move 9 things, earn goes across, everything else except for the last one goes across, and then the last one goes up. So you have to think about this again because you have to implement the case in the assignment where you move more than one thing across. And again, the rules are really straightforward to figure out. You just have to follow them or else you can't find anything. Okay. All right, let's see. So this is our final result. Everybody happy with it? There shouldn't be any issues with it. I believe I constructed it correctly. Now, so like it says here, when you are moving things between siblings that are inner nodes as opposed to leaf nodes, the same basic rules apply. You just have to make sure that you migrate things through the parent. So n and n prime are sibling internal nodes where n precedes n prime, just to keep it simple. Okay, and like it says here, k prime is the search key between n and n prime. So you can always look at the parent node and say, okay, this is the search key that's actually sandwiched by n and n prime. Because you know those page numbers, you can go look for them in the parent and see what actually is sandwiched by them. So you're moving pointer, the last pointer, so n dot p sub m, that's the last pointer in n. You're moving that to n prime, and you're inserting it because that's where it goes. Notice n prime dot k1 is set to the new key. So we slid over all the other keys. I should actually probably make that clearer in the slide. But we go ahead and slide over the existing keys. We bring down k prime. That's the parent's key value. We bring that down into n prime. The last key in the left sibling goes up. That's k sub m minus 1. Because remember, there's m pointers and m minus 1 keys. So that's why it's k sub m minus 1. And then basically, like it says here, n dot k m minus 1. So the last key and the last pointer are both removed from the left sibling because we migrated stuff away. Pointer goes right, key goes up. And parent key goes down to separate the pointer that moves right. Okay? I should draw pictures of this. I was thinking about that this morning, and I should draw pictures to describe these. Because pictures are a lot easier to understand. And then it's like N, K, and M bullcrap. Okay, yeah, and so like I say here, if I'm moving N prime dot P1 to N, so you're moving it left, it's the same idea. N prime dot K1 goes up, K prime goes down to become N dot K sub M, because you're adding 1 to it now, and N dot P sub M plus 1 becomes the pointer you're moving across. Okay, so same idea, whether you're moving left or right. You just have to migrate the key through the parent. Any questions? Alrighty. Let's see, coalescing. So this is our B tree after we've also deleted yak, so there's no more yaks to zap. And now we just have earn and zap in the last value. And so you'll notice here something that if I delete pop or rat or earn or zap, then I have a situation where I can't really coalesce between the leaves anymore. I can't redistribute between the leaves, but I have to coalesce. So I have to combine those, and then we end up with a situation where the right inner node will lose a pointer, and now it'll only have one pointer, so I have to do something with that. I could redistribute, but what we'll do is we'll go through the example of coalescing. Okay, so we delete rat. So this is, we've already talked about it, so we can talk about that. So this is what we get after deleting and coalescing. And like I said, we could migrate off to the right, but we won't this time, because we need to see how this example would work. Again, we have two inner nodes, and they have a parent, and their pointers in the parent, since they're siblings, should be separated by a key. So you can see that we have pop there. And so it's basically just the inverse of what we described before. I move that pointer across, I need a key to separate them. Well, what key should I use? I mean, you can think of this right path as being just, the same path as what we want in the end, but with just an extra hop in it. So we can just pull the key down into the left sibling and then use the right sibling's pointer, and everything will be correct. So we end up with something like this. Now, I don't want you to ask me about this root node and the right thing right now, but let's just look at the left sibling or the left inner node and everything else. Does everything look correct there? So you've got dot, which again we mentioned is that weird anomaly where when you delete a value, it may still appear in inner nodes, and that's okay so far. We have off, which will direct us into the third leaf, and we have pop, which will direct us into the fourth leaf. So everything looks correct. Should be okay. And so now we have this thing. Do we really need that root anymore? We don't need the root anymore. So this is what I love about B-trees is like, okay, it's squishing now because we have enough, we have a small enough amount of data that we don't need the root node anymore. So we can just throw it out. Okay, so we remove the pointer to the deleted node. We just follow the mechanistic process for removing it. And so now you end up with the root node being only one pointer. And we know that if there's only one pointer, we don't need it anymore. So we go ahead and throw that node out or mark it empty so that we can reuse it for something else. And we set this left sibling inner node to now be the new root of the B tree. So you can see that every once in a while you have to touch the header page on the B tree because the root is changing over time. Yes? Which ones have to be at least 2/3 full? They all need to be at least half full. Yeah. Yeah, so here it is, if you think about it in terms of pointers, then the leaves are the ones that need to be at least 2/3 full. Because they can have 3 pointers and at least 2 of them need to be set. It did not need to. Well, I mean, as long as there were 2 pointers in it, because we measure fullness in our examples by number of pointers. Yeah. So even though we had just pop, it still was enclosed by 2 pointers, so it was okay. Yeah. Which is why we didn't really have to coalesce, but in this case, it was kind of nice because it shrank our B tree. And so what you'll notice is the NanoDB implementation, it prefers to redistribute as opposed to coalesce because it's less work. But you can see how there might actually be a benefit in preferring to coalesce instead of redistributing because it'll keep your index as small as possible, which is really nice. I don't know offhand if one of those would require you to restructure the B tree more often than the other, like preferring to coalesce versus preferring to relocate. So that might be another thing that would be interesting to study if you have a hankering for index studying, and there's a lot of good problems to solve that would be very helpful for NanoDB down the line as well. So if you are interested in this kind of thing for 123, that would be yet another index-related problem that you could explore. If preferring to coalesce makes a tree structure change more often, like you get into situations where you remove a node and then you immediately have to add it right back versus removing it and then you don't have to worry about it. That kind of thing. Okay, so here's a sketch of the delete algorithm, and it's horrible, so I'll just go ahead and show this up here. So value k, pointer p, we find the leaf node containing the key and the pointer. Now again, notice, we do that navigate from the root to the leaf as a preliminary step in doing this, because we always start our modifications with the leaves. What can we do? And so when we have this operation that's so common, that's going to be one of the things you have to implement in assignment 5, is just how to navigate from the root to the leaf based on the contents of the B tree node. It's pretty straightforward. So we go ahead and we delete that entry from the leaf. That's what we mean by LKP. L is the leaf, K is the key, and P is the pointer. So here's delete entry. We have our node that we're removing it from, the key that we want to remove, and the pointer that we want to remove. So we search through the node, we find the key and corresponding pointer, and we remove them, meaning we slide stuff over. Because just like with heap file pages, we always push tuple data to the end and slots to the front. In B trees, we always push stuff toward the front, just because we always keep things in order. Not having space is kind of nice, because it allows you to not worry about fragmentation. You automatically take care of fragmentation, but it also just allows you to navigate through it more efficiently. And so if n is the root and only has one child pointer, we don't need it anymore. The child becomes the new root, so we can go ahead and delete the node. Otherwise, we may have the situation where n is not full enough, and thankfully this happens infrequently, so that's a good thing. We try to coalesce with either sibling, if we can. Otherwise, we try to redistribute. So you can see that this prefers to coalesce if it can. Otherwise, it will redistribute if it can. So here's the coalesce case, and this is a total sketch of it. It is totally not detailed. This is like a lot of code in NanoDB just to handle coalesce and redistribute. So coalesce n and n prime, where you'd like to choose it where n is the left node and n prime is the right node, just to keep things simple. So k is a key that separates it. So you go to the parent, you look at the parent and say, what key separates n and n prime? You find it, and then you go and combine the contents, and presuming that n prime is the one that becomes empty, you go back up to the parent, you remove the pointer to n prime, and the key that separates n and n prime. So that now goes away. So you'll notice that we can do this recursively. Delete entry, parent of n prime, being the one that's, you could choose parent of n or parent of n prime because they're the same. K prime, which is the key that separated n and n prime's values in the parent, and n prime is the pointer that's also being removed. And then we delete node n prime. Okay. That's a rough sketch of coalescing. It's really complicated because you have to think about, okay, delete entry is recursive, but now you're dealing with non-leaves instead of leaves, so you have to think about all of that kind of stuff. So it ends up being a little bit more complicated. Redistribute. Again, you have a key that separates n and n prime in the parent. So you need to find out what that is, k prime. And you have to think about, am I moving stuff right or left? And if you are leaves, then it's a different situation than if it's inner nodes. But you also have to propagate the right node's parent key up. So that is true for leaves, so you have to do that kind of thing. So yeah, like it says, move a pointer key pair from the fuller node to the emptier node. And this varies if you're moving left or right, which is, again, another detail that we don't cover here. And then, like it says here, you replace k prime in the parent with the appropriate new key value. Depending on what situation you're dealing with. Okay? So that is, like I said, an unbelievably high-level sketch of the delete algorithm. Once you have redistribution and coalescing implemented, it's a pretty straightforward recursive process to just propagate changes back up the tree on an as-needed basis. So you go down the tree to find where it goes or where it should be, you remove that entry, and then you propagate up changes, possibly removing the root as well. Okay? That's the idea. Yes, like I say here, lots of details we're skipping over. Yeah, so this is basically what I was telling you about before. It's a challenging thing to write in a clean way. I still am not completely satisfied with the way that NanoDB does this. And I would love to come up with a better way of doing it. So that will probably be something I focus on in the future. Unless one of you comes up with a brilliant solution, then I'll just do it, which is always a nice thing. Okay, now we also have this other interesting thing that when we're removing something from the B-tree index, we have to know what record it is that we're removing. And that can be a little bit tricky because we have this issue that, well, maybe values are duplicated or something like that. Now, the thing to be aware of is that the key is what will be repeated. It should be that every pointer is distinct. Because when you have an index, and an index is a table file, and let's presume it's dense, but it doesn't matter. It would be true if it was sparse as well. Every record in the index should have a distinct value for the pointer. Because every tuple in the table that's being indexed should only appear once in the index. Even if the key value is repeated, the pointer value should be distinct. Everybody got that? That's kind of important. So what that means is, like, what would be a super key on the index? Well, a super key would be the combination of both the key and the pointer. The key itself may or may not be a super key because we may be indexing something that's a primary key, we may be indexing something that's a foreign key or some other non-key, but at least the tuple pointer should always be distinct. So P by itself is actually a super key, and the combination, of course, will also be a super key because P is a super key. Okay, so yeah, we simplified the examples by disallowing duplicate values. So here's the question, and this is sort of the thing that you have to think about. The way that we've phrased it so far is that inner nodes, the pointers are just pointers to other inner nodes. The only place that tuple pointers actually appear is in the leaf nodes. And so when you're searching through the index to find that entry that you want to remove from the index, you're using the key, and you may plop out at some place where you have a run of those key values. And so you have to start searching from there to find, okay, does this have the tuple pointer I'm looking for? Does this one have the tuple pointer I'm looking for? Does this one have the tuple pointer I'm looking for? Everybody got it? Because you may have the same key value repeated multiple times. The pointers in the inner nodes are pointers to other inner nodes in the index. They are not tuple pointers. So that suggests an obvious solution, which is, why don't I also incorporate the tuple pointer into my key value so that in the inner nodes I can do a more precise navigation to where I'm going? It has a gross name, Uniqueifier. I don't know who thought that was a great name, but it is the name that we're using. But basically, what we do is we add the tuple pointer into the key as the last value in the key, and there's a lot of good reasons why we do it as the last value in the key. And that way, when we're looking for a particular tuple, if we know the tuple that we're looking for, like we're doing a delete, then we can just incorporate that into the key, and it'll drop us into the B-tree leaf node that will either have it or it's not in the index at all. That's what's nice about it, is that it will direct us exactly to the leaf that should contain it. Okay, and so that's why it's actually really nice. You have this one draw. What's the obvious drawback of this? Yeah, so now my search key values got a little bit larger. In our situation, they got 4 bytes larger. So that obviously reduces the branching factor of our index, which will reduce the performance of queries against the index, because now I may have to drop down more levels than I would have before. But it makes deletions faster. So it's all a trade-off. It's like, do I care about making deletes faster? Do I care about making inserts or updates faster? Do I care about making queries faster? You have to answer these questions when you design indexes. Yes? This will make queries slower to do this because, or it has, I should say it has the potential to make them slower, because since the keys individually, I might have misstated it. I'm a little bit tired today. But if keys get a little bit larger, then it means that you may have a deeper index tree. And remember, the cost of looking stuff up in the index is taking each step down the depth of the tree. So if your depth increases, your query cost increases. That's right, yeah. So if we have a situation where the key values k are not distinct, like let's say it's on a foreign key or something like that, then if we're trying to remove a tuple from that index, then we use the key value and we navigate down and we find the first leaf that key value appears, but then we need to scan through to find the actual tuple itself. Because you may have a run of keys that are all the same value but pointing to different tuples. And so then you'd have to find the specific tuple you want to remove by looking at the pointers, the tuple pointers, and then you'd remove that record. And if you have a situation, for example, where you're trying to design a nice normalized database, and so you have this little table with 15 entries in it that are all your 15 possible values for something, and you have 1 billion records that index into that little table with 15 possible values, well, you're going to have big runs in your index of the same key value. So deleting would be very slow because you drop into the first leaf where that value could appear, and you have to chase all the way through to find the specific tuple pointer of the record you want to remove. So that's where not having this quote-unquote uniqueifier, or in other words, in much simpler terms, just incorporating the tuple pointer into the key, that actually improves deletion performance a lot, because when we start searching, we end up right in the exact leaf node with the tuple that we want to delete, because the tuple's pointer is part of the key. Does that make sense? All right. I feel like people kind of get it. I'm going to have a section that specifically describes this in Assignment 5, because once you say, hey, why don't I just add the tuple pointer into the keys for the index, then it suddenly suggests another thing, because it's like, okay, my inner nodes have key value tuple pointer. My leaf nodes have key value tuple pointer. So why not just store whatever I want in B trees? Why not just use them as a general table format? It just so happens that indexes have a special schema where one of the columns is a tuple pointer, whereas a regular table will just have whatever the person said in the create table command. So you can use B trees as just general table files as well as indexes. Indexes are a special kind of table file with one column being a tuple pointer that you can use to access another table. Does that make sense? Well, if it doesn't, you'll see it on Assignment 5. There's another reason why we really, really want to do that, which is that if we have our indexes being a special kind of table, then it allows us to use indexes to satisfy queries as well as tables. We can do our group by and aggregation stuff on the index because it's smaller and has smaller rows in it. Okay? So there's a lot of benefits of iterating this idea and taking B trees and turning them into a general concept. Unfortunately, I don't talk about this yet. I think I'll probably update these slides before the next time I teach 122 and incorporate this. So anyway, just talking about all of that stuff. All right, so that's enough of that. Let's see, so searching the index. This is where I was talking about how when you are searching an index, we have an ordered index on A, B, and C, columns A, B, and C. We can also access the index on A and B, or we could access the index on just A. And so when we do our indexing lookups, as we navigate through the inner nodes down to the leaves, we just specify a smaller tuple that contains the values that we're looking for. And we do the same thing if we have tuple pointers in our keys. We just don't even specify it. And we fall out at the first place that the key appears in our leaf pages. So like I said, usually the uniqueifier will not be specified for searches. It only appears when I'm deleting something or modifying something. In those situations, I have a specific tuple I want to change, and so I know the tuple pointer, I specify it, and I end up in the exact leaf node. So yeah, that's basically what I've been saying. I've actually been talking about this for the last two lectures, so I won't really spend too much time about it. The other thing that's really nice is, what if you want to do a sequential scan through the index, starting with the first value? Well, one thing you can do is just specify an empty tuple. Because now you're saying, well, I have an empty tuple and I'm comparing it to search key values, and the empty tuple will always be left, so you always take the left pointers and you end up in the first leaf and you run across. Or you could do something more special cased where the root, or I should say the header page knows the leftmost leaf, but then that's extra work. Why not just do the other thing? And there's other reasons, like with concurrency control, that you'd like to do that, but we won't go into that now because we haven't talked about concurrency control yet. Okay, a few other things. String keys, obviously that affects the branching factor. And so the common approach to this is to have your index only use a prefix of the string. And the challenge is picking a prefix that's large enough to be of use, yet small enough that your branching factor still stays quite high. And so we actually briefly mentioned this in 121, that when you create indexes on strings, you can actually say, I only want the first n characters of the string. And so that's this example here, index on customer name, where you say, I'm going to try to just use the last four characters, or I should say the first four characters of the last name and the first four characters of the first name, and that gets you close to where you need to find the value. Yes?
So, strings are stored like ASCII.
Yeah, they're stored. Well, I mean, I guess for us they're stored UTF-8, but yeah, that's
Right. So if we do a little better, right, and compress them somehow to take up a full pieces of bytes per character. Because like if it's only readable characters,
So you're saying like zip compress or some like whatever compression algorithm? Is that what you're talking about? Just applying?
some sort of compression is stuff more than one character. Like,
Yeah, I mean, I like the idea a lot. I guess the only thing is it starts to introduce other overhead, and so you have to again think about the trade-off of whether or not it's worth compressing and decompressing everything. It'd be cool if you had a compression algorithm where the compressed data, well, I guess that's probably not possible, where the compressed data also sorted in the same order that the uncompressed data did, because then you could do a lot of cool stuff. But yeah, I unfortunately don't know enough of the implications of that situation. All right, anything else? Should we talk afterward? Okay, because yeah, I mean it's like 11:58. So, all right, cool. I will see you all on Friday then.